Alright, in this video I'll be doing part 2 of the test for review. So on number 12 here we're dealing with the radical equation, and so in a situation like this we want to isolate the radical and then we'll square both sides. Now sometimes students will actually try to combine this minus 2 with the plus 4 here, but because the minus 2 is under the radical here we can't do that. But what we can do is subtract the 4, and let's get that radical isolated. We get x minus 4 is equal to the square root of 3x minus 2. Now I'm going to go ahead and rewrite this so you can see my steps. And I'm going to go ahead and square both sides. We want to square this side to get rid of the radical, and of course whatever we do to one side we do to the other. Now notice what I did here. I have to square the whole side. I'm squaring this binomial. If you just square the x and the 4 separately, you're going to end up with the wrong answer, because we're going to have to multiply out 2x minus 4's here. On the other side we have 3x minus 2. So when we FOIL this out, we're going to get x squared minus, let's see, we got a minus 4x and another minus 4x. We're going to get minus 8x. And then plus 16 equals 3x minus 2. And at this point, you want to pause and just consider what your strategy is. This is a quadratic equation, so we treat it differently than we would a linear equation where we've just tried to get x by itself on one side. In this case, I want to get 0 on one side and everything else on the other, and I'm hoping to be able to factor this. So let's get rid of the 3x by subtracting 3x on both sides. And let's add 2 to get rid of this 2 here. So we're going to end up with x squared minus 11x plus 18 is equal to 0. Now I'm assuming that you can factor this. We use what's called the AC method. This is a 1x squared, so we know we're just going to have x and x here. And I need two numbers that multiply to 18 that add to negative 11. That would be negative 2 and negative 9. So when you factor that, this is what you get. So we can set each of the factors equal to 0. And you're going to get 2 and also 9. And let me just check. Alright, so let's go ahead and check the 2 here, because one of the things we discussed is how with radical equations you want to check your answers. If you plug in the 2 here, you'd get this here. So notice this is the square root of 6 minus 2. That's the square root of 4. Well, 2, which is the square root of 4, plus 4, that's not going to be 2. So you can see that the 2 doesn't check here. You can verify that the 9 does work. It does check if you plug that in. Let's go on to number 13. Now we learn with radicals, or when we have a radical equation with two radicals, we want them on opposite sides. So let's go ahead and add the square root of x minus 6 to both sides. So we're going to get the square root of x plus 9 is equal to 3 plus the square root of x minus 6. And by the way, it really doesn't matter which of these you put first because it's addition. So now we're ready to square both sides. So again, I'm going to rewrite this equation. And I'm going to square both sides. So of course when we square the square root here we get a x plus 9. Now over here you got to be careful. You're going to have to FOIL two of these guys out. So I'm going to do that over here, off to the side, just to keep this part over here nice and clean looking. So 3 times 3, our first product is 9. And then we're going to multiply 3 times the radical x minus 6. Well, all I can do is put the 3 in front, and notice the inner product is the same. And then we have to remember when you multiply the square root of x minus 6 times the square root of x minus 6, you just get the number inside, which is x minus 6, so plus x minus 6. So notice we have a 9 and a minus 6, that'll be 3. And these are like terms, or like radicals. We've got 3 square roots of x minus 6 and another 3 square roots of x minus 6. That's going to be 6 square roots of x minus 6. And then don't forget this x. And so that's what we get. This is just a side, work on the side. We get 3 plus 6 square roots of x minus 6 plus x when we multiply this out. Alright, so again we need to kind of pause here and think, okay, what am I trying to do here? Well, at this point now I have one radical, and so we know we've got to go back and do what we did, kind of like what we did over here. We need to get that radical by itself, and then we can square both sides. And so that's what makes these take a while. You've got to square both sides twice. The nice thing though is you can see we can subtract x on both sides. And we're going to get 9 equals 3 plus 6 square roots of x minus 6. Now be careful, you can't add this 3 with this radical expression. But I can subtract the 3. Get 6 equals 6 square roots of x minus 6. We can divide each side by 6. So we're going to get 1 equals the square root of x minus 6. I'm going to switch sides here and square both sides. So we're going to end up with x minus 6 equals 1, which means x equals 7. And I will just tell you that it does work. It's not hard to see. If you plug 7 in here, you're taking the square root of 16, which is 4. If you plug in 7 here, 7 minus 6 is 1, and the square root of 1 is 1. And it's true that 4 minus 1 does equal 3, so it does check. Let's move on to number 14. It says in the right triangle, find the length of the side not given. Use an exact answer and approximation, and also an approximation to 3 decimal places. So this is where we're using the Pythagorean Theorem, a squared plus b squared equals c squared. Notice here our b is 2 and our c is the square root of 10. So we don't know a. This will be 2 squared, and c squared is the square root of 10 squared. Let's go ahead and square these values. We'll get 4, and we know that when you square a square root you get the number inside. This is just going to be 10. So we're going to get a squared equals, let's see, if we subtract 4 on both sides, we'll get 6. So we'll take the square root of both sides, and we get a equals the square root of 6. So that's our exact answer, and you can plug that into your calculator. Oops, and I didn't do that, so let me grab a calculator real quick. So second square root of 6 is 2.449. That's to 3 decimal places. So that would be our answer written as a decimal. And in a word problem like this, sometimes it makes more sense to have that number. I mean, square root of 6 is not a number it just jumps out at you, but I know what 2.449 is. It's just about 2.5. All right, let's move on. Let me get my marker here. Doesn't look like I have all the ones I'd like. Oh, here we go. Oh, I've got 2 colors. Okay, so we're supposed to describe where we're increasing, decreasing, and constant on this function. Let me readjust my camera here. So you can see that we're increasing here, and we're increasing here. I like to go from left to right as I'm doing that. You can also see that we're decreasing here. and we're decreasing here. Now, in this area right here, we're actually constant. So what I always like to do is where things change, I'll just draw a vertical line. And so basically, this graph goes forever left. So when x goes from negative infinity until x gets to negative 6, we're increasing. So negative infinity to negative 6, we're increasing. Well, what happens at negative 6? When x is negative 6, now from negative 6 until x is negative 3, we're decreasing. So negative 6 to negative 3. So notice you went to here and then it picks up here. Well, what are we doing now? We're increasing again. So we'll just put a comma here. In some books they put a union there. And it's going to go from negative 3 until we get to negative 1. So again, I want to remind you, these are all intervals of x values. We're describing what the function looks like. You know, it's increasing, decreasing, or constant on what x intervals. Okay, so we went to negative 1, and then from negative 1 until x is 2. So from negative 1 to 2, we're constant. And then you'll notice from now on the function is decreasing. So that occurs when x goes from 2 to infinity. So we'll just put a comma there and 2 to infinity. And these are always going to be open parentheses or parentheses, because at these turning points the function's not increasing or decreasing or constant, it's actually changing. It's like right in the middle. So you'll always have parentheses when you describe where you're increasing, decreasing, and constant. All right, let's move to the last page. On number 16, it says a community college math lab has 30 feet of dividers with which to enclose a rectangular area for a student testing center. If a corner of the math lab is used for the testing center, the dividers are used to form the other two sides of the rectangular area. Express the area of the testing center as a function of x. So let's draw a picture. We've got this corner, and we've got 30 feet of dividers, and they're going to make up the other two sides of this rectangular area. So this is our wall, and these are the dividers. Now there's 30 feet of dividers, so that's basically this part here. We know that adds up to 30. And let's see, what else do we have here? If a corner, let's see, here we go. Express the area as a function of x. Well, let's go ahead and call the shorter side x. So, because see, first of all, we need to have one variable that we use to describe the length and the width here. So we're going to call the width x. So if these two add up to 30, then this would be 30 minus x. It's like if one side was 10, how would you find the other? Well, you would take 30 minus 10, and that would make this 20. So if this were 10, this would be 30 minus 10, or 20. So to find the other side, we just subtract from 30 what this side is. All right, so now we can write an area function since we know the length and the width. We know that area equals length times width. So here we can multiply these. We're going to get x times 30 minus x. Or we could also write this as 30x minus x squared. If you wanted to, you could put the x squared first. It doesn't really matter. Now we need to know what the domain is. Well, we know each of these sides has to be positive, so we know x is greater than 0. And we also know that 30 minus x is greater than 0. Now if we solve for x here, we'd subtract 30. And let's do that. We get minus x is greater than negative 30. And we know that when we solve an inequality, we have to multiply both sides by negative 1 here. We'll have to reverse the symbol since we're multiplying or dividing on each side by a negative. So we'll get x is less than 30. So we have x is greater than 0 and also x is less than 30. So really that means x is between 0 and 30. That is our domain, and which makes sense. I mean, if we only have 30 feet of fencing, there's no way that either of these could be 30. It can't be 0. They have to be somewhere in between that. This could also be written in interval notation, 0 to 30. All right, let's move on to number 17. All right, so this is a piecewise function, and depending on our input, we're going to use one of the three pieces. So basically, we have three graphs, y equals x squared. That's what our graph looks like when x is less than or equal to 0. We have y equals 4. That's the output, or what our graph looks like when x is between 0 and 2, including 2 but not the 0. And then we use y equals x minus 1. That piece of the graph is a line, basically. And that's when x is greater than 2. So if you're finding f of negative 3, that would be less than 0. And so we would use this piece here. We're going to square our input, and you get 9. If we're finding f of 2, let's see, aren't we going to want to use this piece because we are including when x is less than or equal to 2, and here we are equal to 2. And so in this case, our output is 4. So no matter what your input is here, your output will be 4. What about f of 5? Well, 5 is greater than 2, so we're going to use this piece. It's going to be our input minus 1, and so that'll be 4. F of 0, well, for x less than or equal to 0, and our input or x value is equal to 0, we're going to use this piece. And so it'll be 0 squared, and you get 0. All right, we've got one more problem to do. We've got to graph a piecewise function. And let's go ahead and get started. So basically, what you want to look for is what I call a boundary value. Well, you can see that when x is less than or equal to 0, our graph is going to be y equals 1/3 x. But when x is greater than 0, our graph is going to be that of y equals x plus 4. So 0 is the turning point when x is 0, and so that's our boundary value, x equals 0. So we're going to want to find that point on both graphs. So for x less than or equal to 0, we're going to use y equals 1/3 x. Well, let's make a little table of values. And let's start by choosing our boundary value, x equals 0. Of course, 1/3 times 0 would be 0, so 0, 0 is what we get here. Now notice this is the piece that we're going to use when we're equal to 0, so this point is on the graph. We need to pick some other numbers that are less than 0. Let's choose multiples of 3 so that we get nice numbers. So let's try negative 3. If you plug in negative 3, you would get negative 1 here. Negative 3 over negative 3, or negative 3 over positive 3, that would be negative 1. So let's go ahead and put those in. So we've got 0, 0. We've got negative 3, negative 1. And honestly, we could go ahead and draw that line if we're confident our work is correct, but it doesn't hurt to find one more point. Let's try plugging in negative 6. If you put a negative 6 in here, you'd have negative 6 over 3, and you're going to get negative 2. And so that would be here. And you can see our graph looks like that when x is less than or equal to 0. It's just that piece of the line, y equals 1/3 x. Now things change at 0, so when x is greater than 0, we use y equals x plus 4. We use that graph. Well, when x is 0, that is our borderline value. Notice you would get 0 plus 4, which is 4. Now this point is not going to be on the graph because, again, I'm finding this value because it's a borderline value. It's where things change. It was at 0 that things change. We're going to want that point on our graph, but it's not going to be included, so it won't be solid. It'll be open. So it'll look like this. See, when x is equal to 0, we're using the other graph. All right, but let's see what happens from here. If we choose any value greater than 0, how about 1? 1 plus 4, we're going to get 5. And let's do one more. Let's plug in 2. 2 plus 4, we're going to get 6. So 1, 5, and 2, 6 are points on this line. Notice for this line, it's going to look like this. So this is what our graph looks like when x is greater than 0. That's this graph here. So basically, this graph is made up, or this piecewise function is made up of two lines. This one here, for just the part where x is less than or equal to 0, and then we take, from there on, we're going to be using this graph, the one of y equals x plus 4. Notice the reason why we want to have that point right there is because we're going to have everything right up to that point. So this is an important point to show on the graph. And so that's what the graph looks like. And that's going to be it for this video. And just let me know if you need anything else.